Hello everyone. Let's start our next chapter about geology, the study of Earth, and we will be talking about rocks and minerals. To start, let's talk about where all these materials on Earth come from. Our planet is not a uniform ball of matter. It is layered. We can see here in diagram. This top portion is the surface of Earth, and the bottom portion is the core of the Earth. And the Earth is not a uniform, rather it's a layered matter, and because of the gravity, the heaviest materials, primarily iron and nickel, uh, sink and form the molten core. So this the core section of Earth are mostly made up of heavy materials like nickel and iron, and the lighter, less dense material floated upward to form the mantle. uh, uh, to form the mantle, and sorry critical for us, the thin surface crust we live on are also made up of these less dense materials. While the Earth itself is mostly iron, oxygen, and silicon, our crust is dominated by light elements. In light elements, in fact, there are around 8 elements that made up of about 98.6% of all the matters on the crust, and among them we have around 46.6% oxygen, 27.7% silicon, followed by aluminum, iron, calcium, sodium, potassium, magnesium, and some other elements around 1.4%. And if we look at this, we can say that most of the materials in the Earth's surface are primarily made up of oxygen and silicon, and everything we see, for example, every mountains, every beach, every riverbed is fundamentally built from the rocks and minerals that these elements combine to form. And and we will be mostly talking about the materials that made this cross section of the Earth's layer. Let's before we start talking about rocks, first let's define what a mineral is. For something to be classified as a mineral, uh, it must meet a few criterion. First, it must be naturally occurring. We are not talking about synthetic diamonds or lab grown crystals here. And for example, even for a diamond can be found naturally, as well as it can be lab grown. So we are when we are talking about minerals, we are only talking about materials that occur naturally. Second, it must be inorganic, meaning it was not formed from a living organism, uh, though there are some exceptions, such as the mineral uh, exception, apatite. Apatite is a mineral that is made up of materials similar to uh, material that are found in bones. However, in general, the in a The minerals are made up of inorganic materials, and they are generally rigid and solid in shape. And third, like we said, the minerals should be solid. For example, liquid is also inorganic compound, but it's in a sorry, water is also a liquid form, and we don't call it mineral because it's not a solid material. We will only call it a compound, not mineral. Finally, uh, and perhaps most importantly, a mineral must have definite chemical composition and definite crystalline structure. This means minerals has a specific fixed chemical formulas. Like for example, if we are talking about salt, it is always sodium chloride. If we are talking about quartz, it's silicon oxide, SiO2, and so on. More than that, and the atoms must be arranged in a highly ordered, forming a crystalline structure. Uh, in these atoms are arranged in regular and repeating internal pattern, and those are called crystal structure. This internal structure, it is what controls nearly all the physical properties we use to identify the minerals. For example, here uh, we can see that this crystal structure can be formed from a single atom or a multiple atom. For example, diamond is made up of uh, carbon atoms. It doesn't have any other element. And for example, if we are looking at quartz, is made up of silicon and oxygen, forming crystal structures. Let's look at a couple of examples. And crystal in a crystal structure, a mineral's composition can involve, like we said, one or multiple elements. A very good example of single element mineral is a diamond, and multi-element mineral can be quartz. But the truly important idea here is that the arrangement of atoms forming the crystal structure is what determines the mineral's shape and overall physical properties. So basically, arrangement of atoms is what determines the mineral's crystal shape. And in the figure here, we can see different crystal structure for different kind of minerals. Uh, uh, and for example, carbon arranged one way. If we are talking about the arrangement of atoms, for example, if we are talking about just an element made up of carbon, uh, carbon arranged one way forms soft graphite. Graphite is also an element that is made up of only carbon, and if those carbon are arranged a different way, they will form a very hard diamond. So that's a very good example. So carbon can form both graphite or diamond based on how the structure, all the carbon atoms are arranged in the crystal structure. So basically, the atomic arrangement, not just the element themselves, is the key uh, key to defining each minerals. Not just the elements the structure is made up of, rather the uh, composition as well as crystal atomic structure. And the silicates are the most abundant mineral group. Like we said, we talked about how much oxygen and silicon are there in the earth core, earth crust, where here we can see oxygen around 46.6% and silicon 27.7%. So it is obvious that the most abundant mineral group is silicate. And this silicate makes up around 92% of Earth's crust. Their fundamental building block is the silicon oxygen tetrahedron. So the fundamental building block of silicate is silicon oxygen tetrahedron, SiO4, which is shaped like a pyramid. uh, One silicon atom surrounded by four oxygen atoms, and it can be this tetrahedron can link together in different ways, forming major silicate structures which are different from one another. For example, if we have an isolated tetrahedron of silicon uh, isolated silicon oxygen tetrahedron, then we will generally get a mineral called olivine. And then if there's single or double chain of this silicon oxygen tetrahedron, generally it results in uh, pyroxene or amphibole. And then seeds of this tetrahedron forms stacked seeds of this tetrahedron forms minerals like mica or clay. And the 3D framework of silicon oxygen tetrahedron forms minerals like quartz and feldspar. The specific arrangement determines which silicate minerals forms and influences properties of these silicate materials uh, like hardness, cleavage, etc. And the remaining as we said, around 92% of Earth's crust is made up of silicate, and the remaining around 8% of the crust are non-silicates, which are still incredibly important, especially if we are talking about industries and resources, where uh, these non-silicates are very important resources. And this non silicate materials are generally categorized in uh, four uh, four different types based on their chemical compositions. Usually the ion, they contain carbonates. The ion that contains carbonates, which contains CO3 groups, carbonate. uh, the carbonates contain uh, CO3 groups are the most abundant, and these are the most abundant of all these non-silicate uh, minerals. and a very good example of carbonates are calcite CaCO3, which is found in limestones, and if you this limestone is what is used in making cements we use for structures. uh, Oxides are metals combined with oxygen. So basically, metals combined with oxygen. Hematite is an example of very important example of oxides, and this hematite is what we get our irons we use in structures from. So basically, this hematite is iron ore, and it's in the oxide groups of minerals. And then we have sulfides. These sulfides contain sulfur and metal, such as pyrite, or this pyrite is also called fool's gold because of this gold like looks. Finally, we also have this native elements, and these native elements are minerals composed of single elements like gold, silver, copper, diamond, etc. These are made up of one element. To identify minerals, generally geologists rely on physical properties, and the most obvious physical property of these minerals is color. Color is the most obvious, it often the least reliable. So color is most obvious, but it's least reliable. A small chemical impurity can drastically change the color of mineral. For example, if you look at here, a quartz mineral can be we can find quartz that's clear, pink, purple, or smoky based on the impurities it contains. And some of the factors that influences the color are uh, the composition of the minerals, the elements that the minerals is made up of, and if there are any impurities that will also change the color of the minerals. And if there is a crystal defects, it will also change the color. We can see here in the image there are different kind of minerals with different color, distinct color, uh, and a much better way to identify mineral is called streak. The property is called streak. This is the color of the mineral in its powdered form. uh, and this streak is found by robbing uh, robbing the mineral across a ceramic plate. We can see here uh, we have in the left we have a pyrite that produces a black streak on a white plate, and we have a specimen of rhodochrosite here forming a white streak. And this streak is much better way to identify minerals compared to color. Uh, the there is another property called luster, and this describes the luster describes the quality and intensity of light reflected from surface, and this property is also very useful in identifying minerals. In the figure here we can see a different kind of minerals with a different kind of luster. The most common luster includes metallic, glassy, pearly, dull, etc. And we can see here we have diamond with the adamantite luster, uh, pyramid with metallic luster, kaolinite with dull luster. So basically, luster gives us a quick, descriptive way to narrow down the possibility, uh, to narrow down with the identity of the minerals. And then we have the crystalline structure with we discussed earlier, uh, and we said this crystalline structure is what determines the shape of these minerals, and however this crystalline structure uh, doesn't just dictate shape and strength, it dictates how the mineral breaks as well. So the crystalline structure will also determine how these minerals will break, and based on that definition we have the physical properties called cleavage. And the cleavage is the tendency of a mineral to break along smooth flat planes. uh, this happens because the internal arrangement has specific weak bonds along those planes. So basically, if we look at here, we have mica minerals, and if we look at here, there are different planes here, and these are called planes of cleavage. We can see here, if we apply some amount of load, we can easily uh, easily break the crystal structure and form a layer of mica from these planes, basically because of weak bonds along those planes. And in contrast, we also have a fracture, and fracture is the irregular breakage. The cleavage was smooth and flat planes, and however fracture is irregular. uh, uh, Irregular breakage that occurs when a mineral has no planes of weakness. The atomic bonds are equally strong in all directions, and this fracture can be irregular, splintery, or conchoidal. Uh, Here we can see in the image. If you look at here, we can see this splinter kind of breakage, and then we have this conchoidal fracture and uneven fracture for magnetite. Uh, and one more property that's mostly used is the hardness, and the hardness is defined as a mineral's resistance to scratching. So not based on fracture, rather whether we can scratch the mineral or not. And this is measured using hardness scale called Mohs hardness scale. And the mineral and this Mohs hardness scale ranges from 1 to 10, and the if the scale is 1, that means it's the softest minerals, and if the Mohs hardness scale is 10, then it's the hardest materials, like hardest material, that is diamond, and all the other materials are relative in order. We can see here the softest is talc, gypsum, and so on, and the hardest is diamond. And it is important to remember when we are talking about Morse hardness scale is that this is a relative scale, and it's not a linear scale. And for example, diamond is exponentially harder than corundum, that has a hardness scale of 9. So it's not a linear scale, rather it's a relative scale. If a mineral can be scratched by fingernails, here fingernail has an Mohs hardness scale of around 2.5, and if the mineral can be scratched by fingernail, then it's we call it soft minerals. And the example of this soft minerals that we can easily scratch using fingernails are talc and gypsum. And those minerals have a hardness scale of 1 and 2, and then 1 2 3, and then we have and then we use materials, for example a common materials, copper penny, which have Mohs hardness of around 3.5, and if we can easily scratch a mineral using this copper penny, then the Mohs hardness scale will be around and that number, and it will be around 3 and 4. And we can see here minerals like calcite and fluorite are in this scale. And if it can scratch steel or glass, if the minerals can easily scratch steels or glass, and then it's considered very hard. And example are quartz. uh, Basically this Mohs hardness scale allows us to test an unknown material against a non-reference reference materials, and it helps us quickly determine the minerals and help us classify the unknown minerals. Now let's explore how minerals are formed. The first process is solidification from molten rock, and we call molten rock a magma. And magma, when we are talking about magma, first we need to define the difference between magma and lava. Magma is the molten metal below the surface, below the earth's surface. Here magma is below the earth's surface, and lava is on the earth's surface. As these molten rocks cool, the elements starts to bond and crystallize. So minerals will crystallize from molten rocks as it cools, forming different kind of minerals. As this the crystallization process is follows a very specific order, and that order is defined by this Bowen's reaction series. Bowen's reaction series tells us that minerals that form at extremely high temperature, here we can see in diagram, when the temperature is very high, if the mineral starts crystallizing, it will form minerals like olivine. And basically when the molten metal starts to solidify, it will first form olivine, and they are typically low in silicon. As the magma cools, the composition of the remaining liquid changes, and progressively more silicon rich lower temperature minerals like uh, quartz quartz crystallizes the last when the temperature is uh, comparatively very low. This reaction series is the master control over the composition of all the igneous rocks. And when we say igneous rocks, so we are basically talking about rocks that's made up of solidified magma. And the key component, as we said, defined by this Bowen's reaction series, the key factors affecting this crystallization and formation of these minerals are temperature, pressure, cooling time, and as well as availability and concentration of different ions. We can see here the sodium rich materials are solidified at a lower temperature, and calcium rich materials are solidified at higher temperature. So the availability and concentration of ions also determines which kind of minerals are formed during the solidification process of magma. And the second process of mineral formation is from minerals from water solution. This process of mineral formation happens primarily at or near the earth's surface. So this process is mostly on earth's surface. Under Since it's an earth surface, generally it's this mineral forming process from water solution is normally in normal temperature and pressure condition. As we know, water is a fantastic solvent. As it moves through rocks, it dissolves ions. If that solution is allowed to sit, say in a quiet lake or a cave or a shallow sea, the water might evaporate eventually, causing the remaining solution to become supersaturated, meaning the concentration of the the concentration of the solution will increase, forming a supersaturated solution. And when the concentration of dissolved ions get too high, when the concentration is too high, the ions bond together. These ions will bond together, dissolved ions, and they will start precipitating, and they will start precipitate, uh, forming a solid mineral crystal. Uh, for example, the you probably have seen the example of water, salt water. When you evaporate the salt water and salt water, at the end the water will evaporate and you will see a crystal structure of sodium chloride. And the most common example of a mineral forming process from water solution is halite, as we said, is or table salt, which forms when a salty lake or sea evaporates. And we can also find different other materials. For example, in here, this is an example. This is a lake in Bolivia, where lithium is extracted from salt uh, by evaporation. When evaporation, and when the water is evaporated, the concentrate of lithium carbonate are solidified or precipitated, and the lithium is extracted out of sodium carbonate from these lakes. And this lithium is very critical resources, especially in for example, applications like battery manufacturing. Uh, our third major formation process, the first one was from magma or lava, and second one is from a water solution, and the third major formation process is uh, altered minerals, also called metamorphism. And the literal meaning of metamorphism is to change form or altered to change form. This is a critical process where existing minerals are subjected to intense heat and pressure, usually deep underground due to tectonic forces or near a magma intrusion. So it could be either plutonic or volcanic processes that changes that creates a uh, high amount of temperature and pressure, causing metamorphosis of existing minerals. The distinction between other minerals and altered minerals is that the altered minerals is made up is formed from already existing minerals. And this metamorphosis also happens in solid state. It doesn't change from molten phase to solid phase. It The metamorphosis always happens on solid condition. We can see here. It occurs in solid state without melting due to changes in environmental conditions. So whenever we are talking about a mineral that's formed from melting, we are always talking about igneous rock. And the metamorphism or altered minerals are always formed from already solid state minerals. Uh, the metamorphism causes three main transformation. Uh, First, we have recrystallization. Recrystallization is basically minerals grow larger. For example, limestones becomes marble. So recrystallization is at enough temperature and pressure, high enough temperature and pressure, mineral will change, and the crystal structure will grow larger. And the example is limestones changing to marble. And then the metamorphism can also be phase change. The mineral changes its internal structure while maintaining the same chemical composition, but different crystal structure. And we can see example here, uh, andalusite here. We have at this temperature and pressure, it's in this form, and as the pressure is increased, temperature is reduced, and it will change its crystal structure into kyanite. And if both temperature and pressure, uh, if the temperature is reduced and pressure in this range, then at high temperature it will form sillimanite. So at higher temperature it will form it the material the andalusite will be in this crystal structure, and at higher lower temperature it will be in this form, and at temperature between 200 and around 780 degrees Celsius it will be in this crystal structure. So it can the metamorphism can also be phase change. And then we have deformation. Minerals are physically flattened, stressed, or rotated due to directed pressure. Here we can see because of this rock here, this structure is deformed completely. And this is from the Western Genesis region of Norway. This is an actual image from this, I'm not sure how to pronounce this, Otroi rock from Norway. And some of the example of metamorphism are garnet, epidote, talc, graphite, serpentine, and asbestos sources. And now when we are talking about minerals, some minerals due to their concentration and economic value are designated as ore minerals. Ore minerals are those with economic value. So like we said, hematite is what we use to extract iron from its mineral. So that is also iron ore. In simple language, all minerals are minerals. We can mine them profitably. One of the most important ways this valuable concentration is through one of the most important ways this valuable ores concentrate these valuable minerals is through a process called hydrothermal vine formation. So basically, hot, soft, superheated water solution known as hydrothermal fluid coming from this volcanic magma uh, dissolves mineral deep within the crust, and these hot fluids then rise through these small uh, cracks in the mineral, and fractures in the cooler overlying minerals, forming a distinct uh, hydrothermal vine. We can see here in the image. This is a high graded gold ore. This different vines are of uh, gold, and these are formed because of this hydrothermal fluid cooling at these cracks present in the different minerals. uh, the, uh, the hot fluids when the minerals sorry this hot fluids which are rich in minerals, uh, when they cool, they rise through cracks and fractures in the already present rocks. And as the fluid cools, the dissolved minerals, such as if we see in this image gold, silver, lead, etc., precipitate out, creating a concentrated minerals like this, and forming minerals of ore, or are sometimes also called mineral veins. Example: pyrite is made up of iron sulfide, often called fool's gold because of its gold like color. And then we have sulfur sulfide of copper and iron. We have a lead sulfide, and uh, we just saw an example of gold as in a native element form. Now let's move from minerals, and let's talk about the building blocks, uh, from the let's move from the building blocks called minerals to the structure they form, and we call it rocks. Simply put, a rock is a naturally occurring aggregate of one or more minerals. Rock can be one minerals or more than one minerals. For example, the rock granite is an aggregate of quartz, feldspar, and mica. So we can see an example. Let's look at an example. Let's give an example. Uh, Granite is made up of aggregate of quartz, feldspar, and mica. Geologists classify all rocks into three main classes based on how these minerals were based on how these rocks were formed. These three classes are the subject we will be mostly talking, and the rest of the slides. And these three categories are igneous rock, sedimentary rock, and metamorphic rock. Each rock groups here tells up tells us a different story about Earth's history. Let's talk about igneous rocks in more detail. Like we said before, the any rocks that's formed when it's solidified from a liquid phase are called igneous rock, and generally uh, they are formed from the solidification of either magma or lava. And when we are talking about rocks that is formed below the earth surface, it's formed from magma, and on the earth surface it will be made up of lava coming out of volcanoes. uh, the and the igneous rocks can be categorized into uh, two categories, namely intrusive or plutonic, and extrusive or volcanic, and these categories is mainly based on the cooling rate. So these categories of igneous rocks is based on the cooling rate. The intrusive or plutonic rocks cool slowly beneath the surface, giving the mineral crystal plenty of time to grow large. So the cooling process is slow, so the mineral has plenty time to grow, so the crystal structure are generally uh, large, and this results in as we say, since the crystal structure is pretty large, and the overall texture of these rocks are coarse and grained. And example of this kind of structure is granite. And we also have extrusive or volcanic igneous rock. And these rocks formed when the molten rocks or magma lava are cooled rapidly uh, on the surface of on the surface. This quick cooling prevents large crystal from forming, so the crystal structure are generally fine grained or a glassy with a glassy luster, uh, uh, glassy luster as well as glassy texture. And the example of this kind of uh, uh, igneous rock are basalt and obsidian. So basically, the cooling rate is the most important factor that determines the texture of different rocks that's formed from uh, the cooling of magma or lava. And then we have sedimentary rock. Sedimentary rocks are formed at or near the earth's surface. Uh, earth's surface, and this sedimentary rock on the rocks are uh, formed by consolidation of materials. These are forms by the consolidation of materials, usually fragments of older rocks or precipitated chemicals. So it can be made up of already made rocks, or uh, like we said, from the water minerals formed from water solution. It can also be formed from precipitated chemicals. And they are the only type of rocks that contains fossils. So sedimentary rocks is what generally we will find fossils. We can see an example here. This is a fossil rich sedimentary rock. We can see all these fossils here. And this sedimentary rocks are classified in three categories, namely clastic sedimentary rock, chemical sedimentary rock, and biological sedimentary rock. Clastic sedimentary rocks are made of fragments or clast of weathered rock, basically because of weathering and erosion. And then we have an example of clastic are sandstone or shale rocks, and as we said, the a formation process is because of the compaction and cementation of these fragments of rocks, and this process is also called lithification. And then we have chemical sediments, and this sedimentary rocks are for rocks form when minerals precipitate out of a solution, like we talk about the lithium we got from brine solution. And then the another example of a chemical is limestone, calcium carbonate, and then the the table salt is also an example of chemical sediment, and these are formed because of these dissolved ions in the water solution when the concentration is high enough for them to precipitate. And then we also have biological sediments. These rocks are formed from the accumulated remains of living organisms, such as plant matters forming coal, or cells fragments forming uh, limestone. So based on the formation process, the sedimentary rocks can be divided into three categories. And let's talk about the metamorphic rocks a little. Uh, Metamorphic rocks are rocks that have been physically or chemically altered by immense heat, pressure, or hot fluids. So basically, metamorphic rocks are previously existing rock. They are already existing, and they are only changing from uh, one form to other form uh, because of heat, pressure, or hot solution, uh, causing them to either recrystallize or change the phase, or distort or stretch in their structure. And again, the condition to form a metamorphic rock, like we talk in metamorphic minerals, is the same uh, conditions when the temperature is very high enough to cause a recrystallization. The rocks changes its structure and possibly its mineral composition as well, because of its reaction with impurities, or a combination of defects, etc. Basically, the structure of rock will change, and the new formed the rock is called a metamorphic rock. And we can see here in example, here this is deformed rock. We can see clearly there are different layers of different deformed structure within this metamorphic rock. uh, and one thing we should be careful about this metamorphic rock is that though the temperature and pressure are high, they are not high enough that the metal will melt. Again, if the metal sorry, it's not metal. Then again, when the rock is melted and cooled, again that will be igneous rock, not metamorphic rock. So the temperature and pressure should be high enough to recrystallize, not enough to uh, cause a melting of these rocks. And generally, this metamorphic rock is instigated by geological events, and geological events in Earth's history, such as the collision of tectonic plates or intrusion of hot magma into cooler overlaying uh, rocks. So it could be movement of movement of the crust caused by tectonic forces, or it could be because of the exposure of hydrothermal fluids on the already existing rocks. And these metamorphic rocks can be classified into two categories, namely foliated rocks and non-foliated rocks. These metamorphic rocks are in two categories. The foliated rocks are characterized by aligned mineral grains, which create layers or bands, and for example mica, and they will form parallel layers of seeds. This texture is caused by directed pressure, meaning the pressure is not random, rather it's directed in one direction, causing the rock to form a aligned flat crystal structures. uh, or instead of pressure, it could be stress pushing on the rock from other sides. And this foliated metamorphic rocks is very common in plate boundaries. Example, slate, genesis, sites, etc. And non-foliated rocks, uh, so no alignment, and they are typically granular. So they are not aligned, so they generally form a granular structures, meaning their minerals grains are randomly oriented. They are not oriented in same direction. This is usually caused by confining pressure, meaning the pressure on these minerals are equally distributed in all directions, not just in one direction. Or it could be simply very high temperature or very intense temperature. High pressure or high temperature without significant directed stress. And like we said, since there is no single direction of orientation of these rocks, there is no single orientation, rather they are granular. They do not show cleavage on their structure. And if you look at the foliated like a mica, you can clearly see cleaves in their structure. And example of this non-foliated metamorphic rock is quart, uh, quartzite from sandstone, or marble formed from limestone. And then finally we have the rock cycle. The rock cycle is a continuous dynamic process with no true beginning or end. uh, it, it, it describes how rocks forms for how rocks form, break down, and transfer due to internal forces, heat, pressure, melting, etc., or external forces such as weathering, erosion, sedimentation, etc. and and we can say Earth is constantly recycling its materials through this process. And we can see a quick summarized diagram of rock cycle. Here we can see rock in igneous form. Because of weathering and erosion, it will form some sediments, and because of compaction or precipitations, or the compaction like lithifications or some other process, it will form sedimentary rock. And with enough heat and pressure, this sedimentary rock will transform into metamorphic rock. And if this metamorphic rock is heated enough, it will melt, and once it melts, it will form a liquid metal form called the magma. And when the magma is cooled, it will again form igneous rock, and the cycle uh, keeps repeating. So basically, earth recycles all these materials, and we do not know which cycle, which is the starting cycles or the end cycle. Rather, it's a cyclic process, and it keeps repeating. And the rock cycle pathways is generally, as we just described, igneous rocks, igneous rocks changes into sediment, and the sediment gets compacted and form a sedimentary rock, and then this sedimentary rock will metamorph into a metamorphic rock. And this metamorphic rock, when heated at high enough temperature, will melt and form a magma. And as the magma is cooled and it recrystallizes, it will form igneous rock. And however, there are some shortcut paths in this cycle. It doesn't have to follow the cycle exactly. Sometimes igneous rocks can be metamorphed directly, uh, and any rock type can weather into sediment. So even metamorphic rock can form sediment, not just igneous rock or precipitate chemical precipitates. Basically, the rock cycle is the Earth's natural recycling system.